So yesterday, or last time I should say, we talked, or I stumbled my way through simple harmonic motion, kind of talking about how, if we looked at like a pendulum moving back and forth, we could measure how long in time it takes for that pendulum to kind of go away from you and come back. That was called period. Or if we want to know how many kind of back and forth, how many revolutions there were each second, we would call that frequency, measured in hertz. Now, so if I'm just kind of looking, if I'm sitting underneath the pendulum, I would just kind of see the pendulum move up, come back, move down, come back, move up. It's just going to move up and down like that for a while. Where I think harmonic motion gets kind of interesting is when we plot that movement against time. Okay, so this axis here is time. And so plotting that out, we would see the pendulum goes away from us, and then it's going to come back towards us and go away from us. And then it's just going to keep going back and forth. And when we plot it against time, which to be honest with you, I expected that to look a lot worse, we can see that it just forms these waves. These are called transverse waves. We could talk about how we have the distance from crest to crest here. That's wavelength, going to be represented by the Greek letter lambda. We have like amplitude. We have crests. We have troughs. There's all these things we can measure about transverse waves. And these transverse waves are going to move through. So now we're going to transition into talking about waves, whether we're talking about light, water waves, sound waves. All these waves share some of the same properties. They're not all transverse waves. Water waves are transverse. Electromagnetic waves are transverse. Actually, electromagnetic waves are two transverse waves that are, perpendicular to each other. But we're going to get there later on. With a compression wave, kind of the way that we're going to think about those is we're going to have parts where they're super close together. There's parts where they're spread out. And we're talking about like material. We're talking about compression waves are moving through either solid matter, liquid matter, gas, stuff like that. That's what our sound waves are. So there we would have the compressions, and then the opposite of the compressions are they're called rarefactions. And really just know that these kind of correspond to crests and troughs. It's just we don't have the matter necessarily moving up and down. It's just compressing or spreading apart. So let's get to what this video is actually going to be about, which is about wave speed. These things are moving through either material or through space, depending upon what kind of wave we're talking about. Mechanical waves are the ones that move through matter, whether it's a gas, a liquid, a solid. And then non-mechanical waves can move through the vacuum of space. They can still move through materials. Like light can move through water. It can move through glass. What's really interesting with wave speed is the material determines what the speed of the wave is, which is kind of interesting. So for instance, if you look down here at question 1 here, the speed of sound is roughly 343 meters per second. And that's in air, kind of room temperature air. We know that the speed of sound speeds up in colder air and it slows down in warmer air, and that deals with the motion of the particles, how close together they are, how fast they're moving, stuff like that. And I'm pretty sure I got that trend right. But what's going to allow us to determine what that wave speed is, and so this is the big equation for today. So wave speed or wave velocity, just going to use lowercase v, is equal to the frequency, so wave speed, meters per second, it will be equal to the frequency of that wave, which is either, typically we label it with hertz, or the way we could call it is waves per second. And that's going to be times the wavelength, or how long each wave is. And one way we can think about that is typically we measure it in meters, or we can measure it in how many meters is one wave. So looking at it that way, we can kind of see how frequency times wavelength equals velocity, because if I've got waves there and waves there, they're going to cancel out, leaving me with meters on top and seconds on the bottom. It's a very, very basic equation, like most physics equations are. And they just kind of show us that, and keep in mind, like the speed of sound through a material through air, it's always 343. It doesn't matter how high the frequency is or how long the wavelength is, it's always going to be 343. It's going to be constant. The wave speed will always be that. So it allows us to see this trend. If this is constant, if my frequency goes up, so if I'm talking specifically about sound, if the pitch of the sound goes up, the wavelength has to get smaller to keep that velocity constant. And this is true when we're talking about like electromagnetic waves, which have this huge spectrum of frequency and wavelength. The speed of an electromagnetic wave is the speed of light. You know, it's c. It's 3 million meters per second. And that's kind of cool. The fact that, and granted, what's going to determine the speed of light is it in a vacuum, air, glass, stuff like that. And we're going to talk about that when we get to like index of refraction. So I'm getting way ahead of myself here. I'm kind of excited because this is kind of a cool concept that we have this. The speed of a wave is constant based upon the material it goes through, which is kind of cool. All right, so let's actually see this kind of in practice here. So question 1, a piano string tuned to middle C, that's just a note, vibrates with a frequency of 262 hertz. All right, so let's just list out what we have. The frequency they said is 262 hertz. Assuming the speed of sound in air, all right, so they're going to give us the velocity is 343 meters per second. They want us to find the wavelength of the sound waves produced by the string. All right, so we're looking for wavelength. So setting this up pretty easy is just a basic middle school algebra problem. Okay, so we got V there, 343 meters per second is equal to frequency 262 hertz times the wavelength, which is what we're looking for. So I'm going to put the wavelength symbol. You could put X there. So now I just got to get wavelength by itself, and that's pretty easy. We're just going to divide both sides by 262 hertz. And that brings us to, can't do that one in my head. All right, so we're going to go cancel, 343 meters per second over 262 hertz. Now I'll bring my calculator over, and I'm hoping it'd be pretty hard for me to mess this one up, except when it doesn't register the 2. All right, 1.3. Well, we're going to leave it 1.3. All right. So the length of these waves is 1.3 meters. So that's how long the sound waves are if they have a frequency of 262 hertz. And once again, higher pitched notes where the frequency is higher, you know, if this goes up, this part has to go down because all of these sound waves are moving 343 meters per second. All right, so this one's pretty straightforward. Just know that trend, that assuming you're talking about sound in the same material, that frequency and wavelength are inversely proportional. If one goes up, the other goes down. If one goes down, the other one goes up, and vice versa. So with that, these problems should be pretty easy. One other thing. So once again, if we kind of keep in mind this whole period frequency thing, like if we were to sub this in for frequency, we could also find that the sound wave, the wave speed is equal to the wavelength over the period. I'm going to be honest, I've always seen it this way. It's rare that I see it this way because typically if we're talking about sound, it's much more useful to talk about frequency than it is period. That's the last thing I got for you. Good luck.